Hello, let's talk about the bond order in molecular orbital theory. Why we need to know the bond order. Bond order we can calculate using the formula. Bond order is equal number of electrons in bonding molecular orbitals in bonding molecular orbitals. I will write MO to indicate molecular orbitals minus number of electrons in anti-bonding molecular orbitals. Right? Number of electrons in bonding molecular orbitals minus number of electrons in anti-bonding molecular orbitals divided by 2 is we call bond order. So if you get the difference between electrons in bonding minus electrons in anti-bonding molecular orbitals, divide by 2 is we call bond order. So using this formula we can calculate easily bond order. So depending on the bond order we can get an idea about the molecule stability. If the bond order is larger, molecule is very stable. If the bond order is lower, molecule is less stable. And another thing is, if the bond order is 0, according to molecular orbital theory, the molecule does not exist. For example, if we take the hypothetical molecule helium-2. So helium always monoatomic gas. It's an inert gas, so we call noble gas in group 8. So it does not exist as He2. Therefore, the bond order for He2 molecule is 0. Now let's go and draw molecular orbital diagrams for the hydrogen and helium and then calculate the bond order as an example. First I will try to draw the molecular orbital diagram for the hydrogen H2 diatomic molecule. So you all know how we can draw molecular orbital diagrams. I explained in last video. So hydrogen 1s1. So let's draw one hydrogen, that is 1s1 electron, and another hydrogen 1s1 electron. So these are atomic orbitals. So we normally draw the y-axis is energy. Right? Initially we have two hydrogen atoms, atomic orbitals. So these two atomic orbitals overlap to make molecular orbitals. So molecular orbitals are property to the whole molecule. Therefore, we draw it in between to the atomic orbitals. So this is atomic orbital belongs to this hydrogen, and this 1s1 orbital belongs to this hydrogen. However, after we overlap these atomic orbitals, the molecular orbitals we draw in the middle, it is a property to the H2 diatomic molecule. So these form one atomic orbital lower in energy, molecular orbital lower in energy, and another molecular orbital is higher in energy. And again, like we discussed in hybridization, these two, hydrogen 1s1 and this hydrogen 1s1, atomic orbitals overlap along the internuclear axis. Therefore, these are sigma bonding and sigma anti-bonding molecular orbitals. The lowest energy one we name as sigma, or another name bonding molecular orbital. So we name this as sigma 1s because this is a 1s1. And the anti-bonding molecular orbitals also sigma. However, to indicate the anti-bonding, we put asterisk sigma star 1s. So sigma 1s is a bonding molecular orbital. Sigma star 1s is our anti-bonding molecular orbitals. So I write two names. Anti-bonding molecular orbitals, and this is bonding molecular orbitals. Right? Now, according to the Aufbau principle we discussed in electron configuration writing, always we need to fill the electron from lowest energy to the highest energy. So this is the lowest energy one. So we need two electrons, 1 plus 1, 2. So let's put both the electrons in sigma 1s level. because each square can hold up to maximum 2 electrons. Now this is molecular orbital diagram for the H2 diatomic molecule hydrogen. So these two are atomic orbitals. If we combine two atomic orbitals, they make molecular orbitals we draw in the middle. One is bonding, the other one is anti-bonding. Now what is the bond order? Bond order for the H2 molecule, our formula is number of electrons in bonding electrons 2 minus number of electrons in anti-bonding 0. So 2 minus 0 divided by 2 is equal 1. The bond order for H2 diatomic molecule is 1. Now let's draw another molecular orbital diagram. This is for the He2. It is a hypothetical molecule He2. We all know helium is a noble gas. It is normally exists as monoatomic gas, only single atom containing gas, not form diatomics. However, hypothetically, we draw this molecule helium 1s2 2s2 configuration. However, we need only valency shell for bond order calculation. So let's draw 2s2 of helium. This is helium 2s2. So this helium again forms sigma orbitals because atomic orbitals overlap along the internuclear axis. So one is lower in energy, the other is higher in energy. And again the same way electrons filled from lower energy to the higher energy. Here 2 electrons plus 2 electrons 4. So we need to fill the 4 electrons starting from lowest energy molecular orbital to the highest energy. So this is helium 2 molecular orbitals, and these two are helium, both helium atoms, atomic orbitals. So this helium molecular orbital we can name as sigma star, and this is sigma, anti-bonding and the bonding. Now let's calculate bond order for this hypothetical molecule. Bond order is equal number of electrons in bonding molecular orbitals 2 minus number of electrons in anti-bonding molecular orbitals 2 divided by 2. So 2 minus 2 is 0. 0 divided by 2 is 0. Bond order for the helium He2 hypothetical molecule is 0. According to molecular orbital theory, if any molecule's bond order is 0 means that molecule does not exist. So He2 does not exist. It's always form monoatomic gas. It exists as a monoatomic gas, not a diatomic. So I hope you all understand how to calculate bond order using molecular orbital theory for these two first period number 1, hydrogen and the helium. So I'm planning to go through the period number 2 molecular orbital diagram in the next video. Thank you for watching.